Nice modelling question here. A tourist decides to do a bungee jump from a bridge over a river. One end of the rope is attached to the bridge and the other end to the tourist, and the tourist jumps off the bridge. I'm just going to draw a bridge here. In fact, I'm going to draw Bristol Suspension Bridge because that is where I grew up. That's my rough little drawing of it. Okay, we've got the rope, we've got the person at the other end. At time t seconds after the torus reaches their lowest point, their vertical displacement is x meters above a fixed point 30 meters vertically above the river. So let's say this is the lowest point, and then we've got the river down here, and then x is minus 20. So what that tells us is that they're 20 meters below the bridge. In fact, this is x equals minus 20. The river would be where x is minus 30. And then up here is where x is going to equal 0. When t is 0, x minus 20, as I already indicated, the velocity is 0. Now that is going to be the change in displacement with respect to time. So dx by dt is 0 when t is 0. And the acceleration is the second derivative, or the first derivative of the velocity. And that's going to equal 13.6. So there's going to be some tension in the rope. They're going to be accelerating up at that point. And in the subsequent motion, the elastic rope is assumed to remain taut, so that the vertical displacement of the torus can be modeled by this differential equation, where k is a positive constant, and we're asked to determine its value. So what we can do here is sub in our initial condition. It must be that 5k times 13.6 plus 2k times 0, well, that's just 0, plus 17 times minus 20 is equal to 0. And this ends up giving us k equals 5. Now we're asked to determine the particular solution. So I'm just going to write down my equation again, but with k substituted in. 25 d2x by dt squared plus 10 dx by dt plus 17x is equal to 0. Now this is a homogeneous equation. There's no function on the right-hand side, so we don't have to deal with a particular integral, just the complementary function by itself. And we try x equals a e to the kt. You put that in and you get your auxiliary equation. And this, I'm not going to go into lots of detail on this, but we're going to get 25k squared plus 10k plus 17 equals 0. This actually won't factorize, just put it in your calculator. We get a complex solution. Minus 0.2 plus or minus 0.8 I. And that means x is going to equal, x is going to equal e to the minus 0.2 t, then a sine 0.8 t, we take the imaginary part and use sine and cos, plus b cos 0.8 t. I always like to remind people where this comes from. Basically, let's use a different constant. It would be c e to the minus 0.2 plus 0.8 it, but you can separate them like this, and you can do the same with a d and a minus 0.2t e to the minus 0.8 it. And you can use Euler's relation on these two, get them in terms of sine and cos, like you get different constants and everything, but it just works out that you can write it like that. I've proven it in other videos in more detail, but you just got to know when it's complex, you use the real part as you kind of normally would, and the imaginary part gives you the sine and cos functions. So now we can sub in our values, the initial conditions. Remember, x was minus 20 when t was 0. So minus 20 is just going to equal b, actually, because e to the 0 is 1, sine of 0 is 0, cos of 0 is 1. We're there. Now we need to differentiate so that we can sub in our dx by dt, which remember was 0. got to use the product rule here. So I will get minus 0.2 e to the minus 0.2 t when I differentiate this one, and times by this. And then I will be adding e to the minus 0.2 t times the derivative of this. Now in both of the cases I'm going to be times it by 0.8, so I'm actually going to bring that out. Then I'll get a cos 0.8 t minus b sine 0.8 t. Okay, now sub in our initial condition. So 0 is going to equal minus 0.2. And then remember the sign gives us 0, so it's going to be minus 0.2b. Then plus 0.8 times a. And that means that b is going to equal 0.8. Wait, I've already got b. A is going to equal 0.2b divided by 0.8, and that's just b over 4, which is going to give us minus 5. And therefore, x is equal to e to the minus 0.2t. I mean, could we take a 5 out? Oh, no, I don't think I'm going to. Minus 5 sine 0.8t minus 20 cos 0.8t. That is our particular solution. Okay, part C says, hence find, according to the model, the vertical height of the tourist above the river 15 seconds after they've reached their lowest point. Be really careful here. X, remember, is like the displacement from the bridge, but we want it above the river. However, we're going to substitute 15 in. So t equals 15 gives x equals, put it in, of course, make sure you're working in radians, but you should get minus 0.70668. So remember, we've got our bridge, and we're going to be here. But we actually want this height, and the whole height is 30. So it's going to be 30 minus 0.70668. And you lose both marks if you don't do this. And it's so easy to just like rush through it and not think about it. But 29.293, which gives 29.3 meters. Finally, we're asked to give a limitation on the model. Now I'm going to go through what the mark scheme says, and I'm going to put down what I said, which I couldn't find on the mark scheme, so I didn't want to start with it. So you could say it's unlikely that the rope will remain taut, because the person's sort of going up and down. There'll be periods where it's not taut. The model predicts they'll continue to move up and down, but in fact they'll lose momentum. Now I don't really agree with this one, because there's an exponential component which is making it get smaller each time. So that is surely bringing in the fact that they're going to lose momentum. If you try and plot this, you'll get this is like a trig function essentially. So some sort of trig function, but then the exponential is going to mean that it's actually getting less and less. So yeah, I'm a little bit confused by that. You could also say the torus is modeled as a particle. Now, when I did it, when I look for limitations, I always like to think about like the actual results, and I looked at what happened when the time gets large. And although it's going to continue to oscillate, it is going to approach 0. So I said that that was a limitation, because in reality, they're just going to end up dangling, down like you would, like this. Well, not like that, not upside down, but yeah, like this. I'm very good at drawing stick people upside down. So surely it's gonna actually go to not minus 20, of course. That was when it was being stretched by its fullest amount, but surely they're going to dangle at like some other amount, like minus 10 or something, as time goes on. And the model doesn't predict that. The model predicts that they're going to like go to there, but surely they're not going to then be hanging from the rope. They're going to be actually on the bridge itself. So that is what I wrote. I feel like I would get credit for that. I'm just going to put it out there, but I'm telling you what I wrote and also what the mark scheme said. Anyway, nice question.